From what it is to its impact on the world at large, join us as we explore Einstein's theory of relativity and explain it so everyone can understand it. So where do we start with something as big and as complicated as the theory of relativity? I'm sure some of you wouldn't even know what it is outside of its name, which is fine, but I'm sure you do know the man who came up with the idea, Albert Einstein. Einstein is revered as one of the smartest people to ever live, and he helped shape how we perceive both our world and our universe. So it might surprise you that this very brilliant man once started off as nothing more than a patent clerk. No, really, he did, and that's part of the origin story to the theory of relativity. Because one day after doing his work at the patent office, he went on a trolley car to go home, and he would do this day after day after day. This is important because while he was on that car, he would think about the universe at large. He would ask himself questions and try to figure out the answers as best as he could with the information he had. And one day he was going away from a clock tower when he asked what would happen if the car he was on was going away from the clock tower at the speed of light. This may seem like an odd question to ask, but light speed travel is something that scientists are honestly trying to achieve right now, and these questions were truly the building blocks of this really happening. Anyway, back to the clock tower. Einstein theorized as well as realized that if he was moving at the speed of light, which if you don't know is 299,792,458 meters per second, the hands on the clock tower, meaning the minute hand and the hour hand, would quite literally appear to stop in place. But he also knew that while he himself was traveling at the speed of light and seeing everything stop more or less, everyone who was at the clock tower and seeing things in normal time would not see them stop. The clock tower and its hands would keep ticking along as if nothing wrong. Yet in this experiment for Albert Einstein, time had literally slowed down. And it was at this moment that the light bulb went off in his head, because it was through this experiment that he realized that if you go faster and faster through space, you're actually causing time to go slower around you. But how was this possible if time was quite literally a constant force in the universe? To try and answer this, Einstein would look to some of the other fathers of science to try and figure out the missing points in his equation. For example, he looked at the three laws of motion via Sir Isaac Newton. Newton notes that while objects do move at a certain speed, their values are never an absolute, mainly because every speed we go is based on a force imparted on something or relative to something else, such as how a car can go 65 miles per hour on a highway, but that's only because the ground and friction allow it to do so. No friction on the road, you're not going at that speed. Thus why he notes that every speed has to have, in respect to, another force or object that is allowing or perceiving that object's speed. However, in contrast, there is James Clerk Maxwell, the father of electromagnetism, who notes that of all the things in the universe, it is light that is fixed. And as noted, light goes 299,792,458 meters per second. That will never change. That speed is another constant force in the universe. Anyone, anywhere in the world, or even anywhere in the universe, will be able to determine that the speed of light is the same. It won't change. And that's part of the reason why the universe works like it does. Because the speed of light is constant, right? But therein lies the problem, or at least Einstein realized that this was a problem. Because Newton said that no speed in the universe could be an absolute. But then Maxwell counters this by saying the speed of light is always a constant, which means that these two very universal and very accepted pieces of science are at a contradiction, which is something you never want in the world of science, trust me. If you're still not getting the full picture of why this is a problem, here's another thought experiment from Einstein to help explain it. Imagine you're at a train station and you're standing out on the platform when a storm comes. Then out of the blue, two lightning bolts strike on either side of you. Because of your position in the middle of these lightning bolts, you perceive them at the exact same time, and the light reaches you at that same time. Everything sounds good, right? But here's the twist in the equation, as it were. Because now I want you to imagine that you are now on the train passing by the station. and you're watching as someone else is having lightning striking on either side of them. Because you are moving, and thus not still like the person on the platform, the lightning bolts would send their light to you at different rates, relatively to your train speed. For sake of argument, the train is going the speed of light, and your position to the lightning bolts. So as you can see, both laws were right, and yet both laws were wrong depending on the position and situation you are in. For scientists and thinkers like Einstein, this is a problem, because that kind of flexibility isn't what you would want in a scientific principle. This is where the theory of relativity comes in, because Einstein had to figure out a way to make his theory make sense while not breaking either law by Maxwell or Newton. Because if Newton's laws were wrong, then the physics wasn't what we thought they were. But if Maxwell was wrong and the speed of light isn't a constant, then something much different is happening with light in the universe, and we would have a whole bunch of other questions to have. Breaking either would be a problem, and that's when Einstein realized that with a small non-destructive tweak to the Newton's laws, what principles could still be true in the wider world that we live in. He called what he created time dilation, proving that via his theory that time itself can be stretched or scrunched depending on the speed of the person moving through space. What's more, he realized that not unlike space itself, time deserved to be not just a principle of the universe, but in fact deserved to be its own dimension. But as Einstein later theorized, this shouldn't be a separate dimension, but rather a dimension in which both space and time would exist as one. Thus was born his belief in space-time, where space and time were together in such a way that all the events of the universe happened because they were combined. This also helped him paint a different picture of what the universe was doing in terms of its formation and orbits, because most people believe that the force of gravity and other elements help keep solar systems and galaxies together. But for Einstein, he felt that he had the better explanation, mainly in that he felt that space-time itself was being warped by massive objects like the Sun, and that the Earth, other planets, other stars, and the other things in galaxies and systems were just trapped in this valley. A radical theory to be sure, but Einstein truly believed that this would explain much of what was just accepted in the field of space science. If you're having trouble picturing that, how's this for a visual? Imagine yourself on a trampoline. Now imagine that you put a bowling ball onto it. What would it do? Simple. It would sink to the middle, right? Now with the bowling ball in the middle, what would happen if you put a marble on the edge of the trampoline? The answer is it would go into the valley that was created by the bowling ball. Due to the Sun having the biggest valley, it is the center of our system and we rotate around it. But all the other planets in our solar system, and by extension all of the ones in space itself, have their own mini valleys, and that's why the moons of various planets, including our own, rotate around them. But wait, this gets deeper if you can believe it, because this theory of relativity applies not just to the distortions caused by planets, but the masses and gravities of said planets. Because as you move through space, the time is relative to your time, right? Well, that would mean that with planets that have heavier gravities that they experience a time a lot slower than ones with lighter gravities. This was actually a major plot point in the film Interstellar. In that movie, some astronauts went to a world that was on the edge of a black hole, and thus gravity and light were much different. The black hole put a lot of strain on the planet, and by that token, light had a different effect on it because of its mass, gravity, and speed, to the extent that a single hour on this planet was 7 years back on Earth. But let's ask the real question here. While it's nice to know that there are always ways to perceive time outside of the norm, does it really affect us in our daily lives? Well, yes and no. It's a complicated question to be sure, so allow me to answer it the best as I can. While it's true that there are ways to distort time by going faster in terms of speed, the way you're doing it is so small in its dilation that it honestly won't matter to you. But there are ways to notice how time is distorted if you pay attention enough, such as how there are clocks that are always a few seconds apart from one another, despite them being locked in on the correct time. Some are based on mathematical figures, while others are dictated by other forces, so thus there is a disparity depending on how you perceive your time. And if you really want to be creeped out because of how the Earth works in its time, it's technically true that your head is older than your feet, because your feet are closer to the core of the planet where you're being pulled at a faster rate. E=mc² is the now legendary formula that helps show off the theory of relativity. But no matter how you spell it out, it's now a key part of our understanding of space, time, space-time, and the universe itself, even though it does have a kind of a big flaw. What is that flaw? It's simple. Think about the name of this principle, the theory of relativity. Remember, at its core, this is a thought experiment, one that is predicated on having a man-made object traveling at the speed of light. We can't do that right now, and it's unlikely that we'll be able to do that for at least the next few decades, if not the next couple hundreds of years. So until we are able to get into the realms of light speed travel, we're honestly not going to be able to know if Einstein was right. And there are many accredited scientists who legitimately wonder if Einstein is right at all, and what that would mean for the universal principles we believe in if we do find out that this theory is wrong. However, that's not stopping others from taking this notion and seeing how far they can go with it. How so? Well, remember the idea of space-time and how things like the Earth and the Sun are distorting the space-time around them? Scientists are using that concept to see if they can make a ship that can go beyond the normal speeds of our own technology. Basically, they're trying to make the warp engine from Star Trek. But in this instant, the warp part of the engine is to warp space-time around the craft so that it can go incredible speeds, something that wouldn't have even been thought of if not for Einstein and his theory of relativity. To help wrap this all up, you need to ask why this theory matters at all, beyond the potential spacecraft, or even how it may or may not help us understand the universe. Why does it matter? The answer is that it is a question that deserves to be answered. The laws of motion and the speed of light seem like very strong constant things, and yet they directly contradict each other in key ways. How is that possible when they're both proven to be true? Einstein's thought experiments may seem like the musings of a man trying to make his mark in the scientific world, but that's exactly what happened to Newton, Maxwell, and others across time. They had a thought, a notion, a theory, and they took it as far as they could go in order to see where it led them. And for Einstein, it led him to the theory of relativity, which helped him start a very long and prosperous career in science. In 1905, a patent clerk published his science paper, which changed the science and perspective of the whole world. He elegantly explained how space and time are interrelated and gave us amazing insights about moving at the speed of light. It introduced us to the cosmic speed of light of an object. What happens if we travel at the speed of light? The theory of special relativity explains how space and time are linked for the objects moving at a constant velocity. This constant velocity is also the main difference between special and general relativity. When we talk about special relativity, we take into account the objects moving with constant velocity. For example, a car moving on a straight road with a constant velocity, whereas in general relativity, we talk about motion, which is not constant velocity motion. Motion in which the observer could be speeding up or slowing down or going around a bend, which we call the accelerated motion and also known as generalized motion, like motion of planets or any other general motion. The move from constant velocity motion to accelerated motion, it turns out, brings in an understanding of force of gravity. Einstein realized that by including generalized motion that would include accelerated motion, he could get an understanding of the force of gravity in terms of warps and curves. We already discussed about general relativity in one of our videos, and you can go and learn more about it. Now let's talk about some very important corollaries of special relativity. One of the most famous equations in physics comes from special relativity, The equation E equals mc squared means energy equals mass times the speed of light squared. It shows that energy and mass are interchangeable. They are different forms of the same thing. If mass is somehow converted into energy, it shows how much energy would reside inside that mass, quite a lot. This equation is one of the demonstrations for why an atomic bomb is so powerful once its mass is converted into energy or an explosion. This equation also shows that mass increases with speed, which effectively put a speed limit on how fast things can move in the universe. Simply, we can say that the speed of light is the fastest velocity at which any object can travel. As an object moves, its mass also increases. Near the speed of light, the mass is so high that it reaches infinity and would require infinite energy to move, as we have discussed earlier, thus capping how fast an object can move. You all might think that's how light travels at that speed. The only reason why light moves at this speed is because it consists of photons, which have a rest mass of 0. As an object approaches the speed of light, its mass becomes infinite, and also the body contracts in the direction of motion. This cosmic speed limit has been a subject of much discussion in physics and also in science fiction, as people think how to travel through vast distances. In fact, Einstein realized that the answer is both space contracts and time dilates or slows. Why? If I'm sitting in my room on my study table, you would say that I'm not moving, but in fact I am moving, just not through space but time. Time and space are interchangeable, or we can say they are two sides of a coin. So when we move through space, some of the motion can be thought of as being diverted into motion through time, and vice versa. In much the same way as a car traveling northwest diverts some of its northwards motion towards west. Space and time are interrelated, somewhat like x and y axis, as shown in figure below. The only difference is that we cannot move only through space. We move through time also. We always move through time. When we are at rest, we move only through time, but when we move through space also, some of our motion through time is diverted towards space, and so the time is less than that it should be, or we can say time is dilated. Thus, the dimension of space and time affect each other, and both space and time are thus relative concepts. This revolutionary idea also helps in better understanding of simultaneity, but we will come to that later. The concept of time dilation is one of the most fascinating ideas in physics. A strange conclusion from Einstein's work is that time moves relative to the observer. An object in motion experiences time dilation, meaning that time moves more slowly when one is moving than when one is at rest. Therefore, a person moving ages more slowly than the one at rest. We can simply say that moving clocks run slower than those at rest. How? Well, as I have explained above, that when we move through space, some of our motion is diverted from time to space, and time moves slower. For a person moving, time would move normally for him, but when observed from a different inertial frame, which is at rest, it would appear to be moving slowly. This becomes extremely apparent at speeds approaching the speed of light. Imagine a 15-year-old traveling at 99.5% the speed of light for 5 years, from his perspective. When he would get back to Earth, according to NASA, he would only be 20 years old. His twin on Earth, however, would be 65 years old. This is also called twin paradox. So an astronaut, Scott Kelly, spent nearly a year aboard the International Space Station in 2015-2016. His twin brother, Mark Kelly, aged a little faster than Scott. To some extent, you can say that the quicker or faster you go, the slower you age, and therefore the younger you are. The reason it's not noticeable in everyday life is that we move with velocity much smaller than the speed of light. The nearer the speed of an object approaches the speed of light, the more warped lengths and time intervals tend to become. While this time dilation sounds very theoretical, it does have practical applications as well. If you have a global positioning system or GPS receiver in your car, the receiver attempts to find signals from at least 3 satellites to coordinate your position. The GPS sends out timed radio signals that the receiver listens to, triangulating its position based on travel time of signals. The challenge is the atomic clocks on the GPS are moving and would therefore move slower and also move faster due to weaker gravity, because gravity also dilates time. We will discuss this aspect in general relativity. But overall, they move faster than clocks on Earth, creating timing issues. The The clocks in our space are ticking faster because the GPS satellites are above Earth and experience weaker gravity. So even though the GPS satellites, which are always moving, experience a 7 microsecond of slowing every day because of their movement, the results of the weaker gravity causes clocks to tick quicker for about 45 microseconds faster than the ground-based clocks on Earth. So now when we add the two observations together, it leads to the GPS satellite clock ticking faster than a ground-based clock on Earth by about 38 microseconds every day. So engineers do have to make the clocks on a GPS tick slower. The amount of length contradiction and time dilation is given by the Lorentz factor. The Lorentz factor is given by this equation. The Lorentz factor, or Lorentz term, is the factor by which time, length, and relativistic mass change for an object while that object is moving. So if an object is moving with velocity c, we put its velocity in the equation, which gives us the factor of how much it will be affected by its velocity. When this velocity v is equal to c, we can clearly observe from the equation that y will approach infinity. So we can assume that traveling at the speed approaching the speed of light would hypothetically enable time travel into the future, as time slows down for the speeding object in order to prevent the cosmic speed restriction of the speed of light. A corollary of all this is that if it were possible to exceed the speed of light, then we could go back in time. It is shown in the TV series The Flash, although some scientists believe that some as of yet undiscovered laws of physics may intervene to prevent such paradoxes. Actually, special relativity does not forbid the existence of particles that can travel at speeds faster than light. And there's a theoretical subatomic particle known as tachyon, which might spend its life traveling faster than the speed of light. However, it's still hypothetical. Another corollary of the special relativity is simultaneity, or relativity of simultaneity. It states that one person's interval of space is not the same as another person's, and time runs at different speeds for different observers. Simply, you can say that if two events occur simultaneously in an inertial frame, then it is not necessary that they will occur simultaneously in another inertial frame. The idea that events that appear to happen at the same time for one person may happen at a different time for another person. The idea of space-time plays an important role in its understanding. We know space and time are interchangeable, and how. The idea becomes even more clearer when we consider that our picture of the moon is actually what the moon was like 1 to 1.4 seconds ago, the time light takes to reach the Earth from the moon. Our picture of the sun is actually how it looked 8.5 minutes ago. And by the time we see an image of Alpha Centauri, our nearest star system, it's already 4.3 years old. We can therefore never know what the universe is like at this particular time. And the universe is clearly not a thing that extends just in space, but in space-time. Therefore, we can say that time is experienced individually. There is no time, there are times. Due to the relativistic effects of the concept of time dilation, our idea and understanding of now is therefore something of an imaginary concept, one which we as humans have devised for ourselves, but for which nature itself has no real use. Physicists do not regard time as passing or flowing, and time is not a sequence of events which happen. The past, present, and future are just there, laid out as space-time. The twin paradox mentioned earlier is the perfect example for this. Therefore, as Einstein remarked, for us physicists, the distinction between past, present, and future is only an illusion, however persistent. Einstein's theory of relativity introduced us with some of the most important underlying theories of modern physics, which open new doors of possibilities to explore for us.